Let me introduce Rebecca Hounsell, who will be telling us about the future of cosmology.
Okay, thank you very much. Hello, everybody. I hope you all enjoyed your scones. I'll give you a minute to get settled. But yes, my name is Rebecca Hounsell. I am a research scientist at the University of Maryland, Baltimore County, working at NASA Goddard. I have four co-PIs for the Roman Supernova Cosmology Project Infrastructure team. There are four of us because we have a lot of work to do, as we all do. So I'm going to be giving this discussion about the future of supernova cosmology with Roman and what we do. And I'm giving this on behalf of our very large and wonderful team. Okay, so bit of a, why are we wanting to look at type 1a supernovae with Roman? So we have thought for the past couple of decades that we live in this lambda CDM universe, this cold, dark matter dominated universe, and we've used a bunch of different probes in order to help us figure this out. So we've got CMB, baryonic acoustic oscillations, type 1a supernovae, obviously, which I'm interested in. And all these things have kind of tried to confirm that we live in this, like I say, this lambda CDM universe. And that's been the current theory for about 20-ish or so years, I believe. And people have looked into different types of alternatives and things and tried to figure out ways, different equations to determine these different types of cosmological models. And, it's going back, okay. Still getting the hang of the pointer. Okay, and so one ways in which people have tried to, parameterize, the consistency with these different kinds of models is through this equation of state and figure of merit. So they have this P, which is a dark energy pressure, rho, dark energy density, W, the equation of state parameter. And for a cosmological constant, you have this W naught equals -1, WA equals 0. W is kind of like talking about potential evolution of things. And we're talking about a decade ago, there was this wonderful plot that's shown here, which was taking all these different cosmological probes and plotting with this cosmological contour and trying to determine, what were these values, and they came up with these numbers, also a bit of a delay here, for W0 and WA, which is pretty consistent with this lambda CDM universe. And they also came up with this wonderful parameter, which we call figure of merit. So different from the rapid figure of merit from I was talking about before. This is the dark energy task force figure of merit. And this is meant to be the inverse of the 95% cosmological contour as shown here. And so the smaller the contours, you kind of want a tiny dot. Let's imagine this green dot. The smaller, the closer to this -1 and 0 you would expect it to be if you're thinking about this lambda CDM universe. And so the figure of merit back 10 years or so ago was this 32.6 or 22.9 without type 1a supernova. And I do make that distinction here because obviously that's what I'm interested in. And we kind of want to get to a whole other place with Roman. So again, when I'm talking about 10 years ago, the number of supernovae that were really used in these analyses was about 740 spectroscopically confirmed type 1a supernovae out to about redshift of 1.3, with Hubble kind of going into the higher redshift end here. And so this is, the distance modulus and the Hubble diagram and the residual plot that you show here. And yeah, this is getting you out to your 32.6 in this dark energy task force figure of merit. There have been many type 1a surveys. Hands up if you have worked with data from any of these. Ah, wonderful. So you know what I'm talking about then. Great. And today, so as of 2022 and 2023, these are published papers, Pantheon by Dylan Brout and Union 3 by David Rubin. This was the spectroscopic sample that we were looking at here. So still, going around to, some of these objects here are going out to about redshift 2-ish, maybe, but a very limited redshift range that we're kind of exploring here, but lots and lots of objects, like 2,000 or so objects. And when we get to the DES 5-year results, this is the photometric sample that was used here. So this is like 1,600 or something, I believe, objects. And this is what things looks like in this way. So you have what is the CFA-CSP foundation sample, which is this lower rung here. And then you have the DES supernova sample, which is this higher range here. And recent results have indicated this could be a little bit different than what we expected. Maybe we don't live in this universe that we thought that we do, but we might actually have this we're kind of moving away from this -1 and 0 thing to quite a significant sigma which is really interesting. We've entered this quite interesting, I'm going to keep using that word, period of time where, as of, this was a slide that I've taken from Brody Popovic. This is the, I never have to say this properly, Dvoki, please correct me, sample. Thank you very much, Dvoki sample. And so this is actually saying, yeah, dark energy might be evolving. Something odd is going on here. Okay, think things are not quite as, I guess, simple as we thought. So Roman, so what we're to talk about. What is it going to do for us? Well, it's going to provide a statistically significant sample of extremely high quality type 1a light curves and prism spectra. Going to cover an extremely broad redshift range. You've heard talks here from, rapid and rise, talking about going out to really high redshifts. And it's over many band passes, and this is one instrument. So we have going from the R, which is F60, 062, and potentially out to K, although we're not using that specifically in this. But yeah, going really quite a broad range of wavelengths. So just want to show here. So this is a slide that I've shamelessly taken from the project, which is really illustrating Roman's high latitude time domain survey. So this survey is these tiny little red-orange dots, the Ithian, down at the bottom and at the top here. So this is Elias North, this region up here, and this is Euclid Deep Field South, I believe. And the high latitude time domain survey is going to be having some wide and deep imaging in bands going through the R all the way up to the F. And it's also going to having prism spectroscopy, and that's only going to be happening in the southern hemisphere here. The exact way in which the survey is going to be planned out is that we're going to have this pilot visits. These are going to be 8 epochs, which are going to happen, shortly after launch, as the mission is starting. You're going to have some of these extended visits here. The core component that's really going to start happening towards the middle of year 2, and then the extended visits out there. And the pilot is really going to help us to get, the templates. It's going to help for doing the different imagings that we were talking about beforehand, as Jacob was talking about earlier. And it's going to really help us establish, what the survey is going to look like, help us prepare, getting this data, understanding the data. The extended is really designed for, looking at potentially at these very long duration transient events that would be happening over the course of the mission's lifetime. And then the core component is going to be the bulk thing for finding, all these very exciting different kinds of transits, and from my perspective, the 1As. And so it's going to be 30 hours every 5 days, 18 square degrees for imaging, and 4.5 square degrees for the prism, which is going to be in the south. Now, the Roman supernova sample. So this is really going to be, this is showing you the respects to the Pantheon sample that we were talking about beforehand. Is the pointer working? Okay, yeah. So this is the Pantheon Plus sample that was there beforehand, and this is going to be the distribution of the Roman sample. So you're really pushing out again into this redshift space. And then this is an image that was taken from Rick Kess's 2025 paper, which was basically using the design that was put forward as part of the core community survey process. And this is showing what the wide field distribution of supernovae is going to be versus the deep field, and how that overlaps with other things that people might be interested in using, so such as the sample from Rubin, essentially, which provides this lower arm anchor, and that's why we're so interested in how we might be able to share data between the different surveys. Now, what kind of quality light curve should we be expecting? Well, really good quality light curves we'll be expecting from Roman for these type 1a supernovae. And these are going out, as you see, wide and deep, going out to redshift 2 that we have here, but even up to redshift 3, we're going to be getting some really good quality light curves from Roman. And this is data that's produced by David Rubin. I believe he puts these in his paper, which is in this 2025 paper as well. And so what does this mean? Well, we're really interested, as I say, in this W0 WA plot. These are the results that you would that have been shown recently with the DES 5-year sample. Sorry, the DESI is shown here. And Roman could help us figure out whether we're up here, whether we're more down here, and should really help to reduce the size of this cosmological contour. We did a couple of playing around with the different types of cosmology, whether we're using a lambda CDM versus the one that's in, say it for me, Gotham. Deveki, thank you very much, and how much it might reduce this region. I'm going to keep using you for that, thank you. Reduce the size of these contours. So this is what we're really going for. Roman is going to help drastically shrink this contour, improve the figure of merit, because Roman is a stage 4 dark energy mission. So previously when I was talking to you about 10 years ago, these were the stage 2 missions. This is the 32.6 value. As a stage 4 mission, we have to increase that figure of merit value by a factor of 10, which means reducing the uncertainties on those W0, WA parameters by a factor of 3. So we're really looking for high quality, well understood, well calibrated data to use within our cosmology analysis. So how are we going to go about doing this? So as I said, I'm one of the 4 co-PIs for the Supernova project infrastructure team. And what are we doing to help to try to ensure this for the community? So our team is pretty large. It's actually got, I think, something over 60 people. And for those of you in the room, so there's quite a few of us who actually managed to attend. I believe Nowers are coming later on this afternoon. I have circled you all with lovely purple circles and stars. But for the purposes of this as well, so that people in this audience can come and harass you later about the work that we do, could you please put your hands up? Excellent. Thank you very much. Appreciate you all. And Skylar, if you're in the room, no. Excellent. You also need to put your hand up because you're also on. So you're hiding. I love it. Behind the pillar. Okay, so we have a wonderful group of people worldwide, people who are contributing to make this mission, this data successful for the community. So we have a website. We talk about this quite often. It's not the best website, but we have a website. So if you want to learn about what we do, if you want to get involved, if you want to comment on what we're doing, there are lots of different ways you can do that. You can go to our website, which will tell you about what our objectives are, what our deliverables are. It will also link you to papers that we have that are published, and also our GitHub, where we're running and doing things. And additionally, provide you with a way to communicate with us. So we have a Gmail. It does not say spit. I didn't think about putting a hyphen in between. I should have done that. But Supernova Pit, to clarify. So that is our email address. This is our website name, and that's our GitHub repo. Please go and check out our GitHub repo. We have lots of tools there for you. And also, we want you to test our code. We want you to break it. You want us to tell us, oh, that's stupid, that's dumb, don't do it that way. We want you involved. We want you to help us build a better pipeline. Okay. So what is it we are tasked with doing? Lots of things, but some of the main things we have are listed here. So we said that we would simulate data to develop, verify, and validate our pipelines. We would do photometry and spectroscopy extraction and data processing. We would do transient classification, because obviously we just are interested in the 1As. We consider the other stuff junk. I like other things too. But for the purpose of what we do, we want the 1As. Importantly, calibration and characterization. We need to fully understand both physics of supernovae, but also things to do with the instrument and issues surrounding that, because obviously when you look at things on sky, you're not going to get truth, you're going to get other things that affect the values that you get. And then produce tools, cosmology, so that when we have these amazing light curves and spectra, that you, the community, can go away and go, okay, I'm going to use this tool that they've also provided us with and derive really cool cosmological results. So I'm going to give a bit of a, I've got 11 minutes left, I'm going to give a bit of an introduction to some of these tools and some of the things that we've been doing. So as part of the work that we did with the Core Community Survey definition team, we created this cool little tool where we provided results of the many hundreds of different simulations that we ran, so different designs, and provided some statistics about that, but also created light curves and spectra for type 1a supernovae, core collapse supernovae, and a bunch of different kinds of objects as well. So if you want to have a look at what you think your redshift 1, whatever supernova might look like, take a look at this tool. It will give you some indication of what kind of signal to noise you're going to be looking at. This was produced very kindly by Rick Kessler and Rob Nope, who are on our team, and there's information and links to the tools there. And then also we have are, as I say, these are catalog simulations. So these are making the light curves and the spectra. And also what we have is Hourglass 2. So has anybody heard of Hourglass 1? A few people. Okay, so a while ago, we've been doing this for a while ago, our team created Hourglass 1, which was with the current understanding of the survey. We created the light curves and spectra that you might get for the supernovae, given our current understanding of the survey. With the CCS, that definition changed. And then Gillian here, if you want to put your hand up, because you're going to be giving a talk later on, decided to take that design and rerun the simulations to produce more realistic forecasts for what the light curves and distributions and things would actually look like. So they're going to be talking later on this afternoon. So I won't talk too much about that. So those are our catalog level simulations. If you don't want to, we use that, create that stuff using a code called SNANA, which is a supernova analysis package, which can be, have any of you ever used SNANA? Okay, a few of you. How, on the level of 0 to 10, how intensive and difficult would you say that that tool is to use? Seeing a lot of 10s. Yeah, let's be honest. So for a more user-friendly experience, if you would like to make your own light curves using the high latitude time domain survey design, we have a tool that has been created by Midai over at University of Pittsburgh, which is called Light Curve Links, I believe. Yes. So if you want to go and check out this URL here, there's actually a notebook that you can use that kind of walks you through making some of your own light curves here as well. And they worked with Space Telescope in getting the APT and understanding how to develop things. So big thanks to Space Telescope there. Additionally, we've been doing things like making pixel level simulations. If you here are familiar with the Open Universe simulation, we talk about it a lot. There's been lots of discussion about it today. Some people are sick of it. I fully understand. Open Universe, you can't see it quite so well here. And maybe I'll go back one just to see if you can. But these were developed by a bunch of different people, but big thanks to Michael Troxell over at Duke University. Very big thanks to them for all the work they did on this. And this is basically simulating a bunch of high latitude time domain surveys, other surveys and stuff as well. And all the little dots that you'll see going off on the screen, these are supernovae, the actual supernovae. And so we've been using these to help to build our pipeline, because obviously to build our pipeline, we need some data to test and do things on. So this is version 1. Version 2 is being worked on right now, and version 2 is going to include a bunch of different things, so a bunch of different effects, as I understand it, and a couple of other modifications to the code. And Troxell is working quite hard on creating this now. So if there's something or some flavor of systematic or other effects that you would like to be included in this data that currently isn't, please contact Troxell and discuss this with them to see if you can get it included in the version 2.0. Additionally, we have been using Roman ISIM, and a huge thanks again to Space Telescope and to Tyler Desjardins for the work that they've been doing to help us create a bit more of a batch processing code to make up these high latitude time domain images with transit sources injected into them for us to build stuff off. So we've actually managed to get these new images, and we're going to produce quite a lot of them. And this started happening as of this week, actually, because we're doing some version 2 testing of our pipeline. So we now have this in place, and we're doing some batch processing, like I said. In addition to doing imaging stuff, though, we also need to look at the prism, because we're going to be using that quite a lot as well. And so this is work that's being done by a bunch of the folk over at Duke and at Space Telescope, who are taking the Open Universe simulations and injecting the trace for the prism into these simulations, but we're using the Roman data model and working on different versions of this for the project and for folks at IPAC. So those of you who are interested in what we're doing with this, can please see me at lunchtime, and I can talk a bit more about that as well. When these data are complete, or a version is complete, we'll plan to make these public as well so that other people can use them and create their own simulations too. Okay, so now we have our catalog level simulations and our image level simulations. What are we doing in our pipeline? Well, we need to detect. We're going to rely on Rapid for a bunch of our detection of supernovae, but we need to detect, and we also then need to do photometry. And so we have a couple of different ways that we're doing that. So one of which is Frosty. I'm not going to say what that acronym stands for, but that's being led by Lauren Alderati over at UMBC NASA Goddard, and also Lee Hu, who's over at UPenn. And so Lee worked on the SSFT component of this, and Lauren has worked on the GPU optimization, hence why I was so interested in the GPUs. Thank you very much, Stella. And this is our kind of our difference imaging and fast photometry kind of thing. So this is some of the latest results that we're having. And so we have quite good precision on this, and it's only getting better with the additional tests that we're doing. If you want to learn more about that, please check out the GitHub and the paper that Lauren put out as well. And now we also have the thing that we're going to be using for much more precise photometry. And when we talk about precise, we're talking about the millimag level. That's what we want to get down to. The reason being is we need to have, you know, these very precise measurements for our good cosmology, reduction of those W0, WA errors. And so the next crown jewel is Campari. And this is being worked on by Cole, who's there. So you can go and harass Cole at some point if you want to learn more about this. But this is our scene modeling pipeline, and we're getting down to precisions of about 5 millimag accuracy, so close to like DES level of accuracy as I understand it. And we're only going to improve upon that in the future. And again, URL there for you to learn more about that. Then we obviously have our spectroscopy. Now, the fun thing about spectroscopy is lots of nice contamination from your host galaxy, so you need to remove that. And what will happen with Roman, with the prism, is actually you're probably going to get like 72 rotations, because you're going to go back to view the region multiple times, obviously over the period of the survey. And you can use that to advantage to almost build up like a data cube of the host galaxy and then subtract that out. So this is work that's being led by Massimo over at Space Telescope. And this is just walking you through some of that building up of that IFU-like data cube and the residuals, which is down at the bottom, which are very, very limited, that you might obtain from that. Now, there's a paper that's being worked on them right now. Hopefully, we'll go in the archive soon. But yeah, feel free to look at the QR code to learn more about that as well. And then from that, obviously, you want to do extraction. So this is work that's being led by people over at Jig and Space Telescope, so Jyotika and James. So we have this extraction of from the 2D sample, 2D to the 1D of the prism, and the different the methodology we're using there, again, explained by the QR code. But yeah, we're getting better at extracting the supernova spectra from our prism information. We're also really interested in characterizations, classification of different things as well. And so we're going to be using SCONE, which is something developed by Helen Q for our light curve classification, which works pretty well. So again, Ori, we can have a conversation about different machine learning algorithms and things like that for light curve things. But for spectroscopy, I'm putting up here some work that's done by Mitchell Dixon over at University of Hawaii Institute of Astronomy. And this is showing here the technique that they're using, which they've called Strider, which I love as a name, and essentially looking at how they're obtaining the classification and the redshift information using time series information. So have any of you looked at the prism spectra that you will obtain from Raymond? I see one hand. Okay, great. People on the pitch should have put your hands up. I'm just, okay. So the spectra are going to be useful to being analyzed in a very much time series way, taking full use of that information from the supernovae. And that's kind of the analysis that we're doing here in order to derive the classification and the redshift. And it seems to be working pretty well, but this is only work that's just really been started. So I expect even more greater things to come. And then the other things I want to talk about in the last minute or so is calibration. And I could talk all day about calibration, lots of things to discuss. But I really want to highlight here some of the work that's been done by Rajita over at Boston University with Dylan Bratt, her advisor. So, anybody seen this image before? A couple of you. Okay, this is the Roman detectors. Beautiful, I know. They have some fun little things on them. You see some nice structure, maybe some adhesive on the sides, a couple of different things there. So these are all have their own beautiful, beautiful characteristics. And we need to understand them for lots of different reasons. Because the way when a supernova lands on the detectors, the knowledge for the color of that supernova might change depending on where it lands on the detector and, even potentially on the time because of other certain calibration issues. And so you really need to have a good understanding about how your detectors work and things you need to consider, because if you get a change in color, it can change your understanding of the redshift and mess up your cosmology. So there's been a bunch of work that's been done, like I said, by our folks over at Boston University, where they've been looking at things like, when the light goes through the focal plane, hits the detectors, how does that actually affect things? And the plot that's shown on the left is a shift in the mean wavelength of a filter that a supernova or any object would have depending on which detector it lands. And so it's detector and filter dependent. It's quite a big shift, as you can see. And the one that's shown on the right is a supernova that was simulated and looking at it over a period of time, so 20 days from peak and then 60 days past peak, and seeing how the magnitude changes as it moves across the focal plane, essentially. And so there are lots of different effects, I'm saying, that need to be thought about here and how we can correct for them when we, in our magnitudes of our supernovae and then in our cosmology results. Okay, so talking about cosmology, the fifth thing, as I said we would do, is our tools. So we have a tool that I'm going to highlight here very briefly that's been developed by Vivian Miranda at Stony Brook University, which is working on emulators, which is a quick way to combine all your different cosmology probes and get your results out. And then the last slide I'm going to show is this. Let us know. We don't operate in a vacuum. Let us know what you need. We want you to have the best products available. So email us, talk to us, check out our GitHub, test our tools, come talk to me at lunchtime on the coffee break. We're here to help. Thank you very much.
Thanks, Rebecca. We have no time for questions right now. We will go to discussion.